Hello everyone. In this tutorial I want to give an overview of perceptual representations in robotics and how they interact with robot actions and the physics of the environment the robot is interacting with. This tutorial is designed from the viewpoint of my students and my experience on perceptual representations for a variety of robotic tasks. This tutorial doesn't claim to be complete, but I hope that it is nevertheless useful to those of you who are interested in representation learning from the viewpoint of robotics. I start this tutorial by first asserting that perception is not passive. It is not just seeing. Perception consists of actively looking and touching, especially when we think about manipulation tasks. Perception is shaped by our task and our expectations on how the world behaves upon physical interaction. There is lots of evidence from cognitive science for this. Let me give you a few examples. So, for example, there is evidence that humans exploit multiple modalities for perception. Here's a study by J.J. Gibson, who's more famous for his work on affordances, which he presented in his book, The Senses Considered as Perceptual Systems. So human subjects were supposed to find a reference object among these sets of irregularly shaped objects. These human subjects were, turns out, most successful if they could actually touch and rotate these objects instead of just passively looking or only visually rotating objects. So this suggests that humans really exploit multi-modality that is only available through physical interaction. Furthermore, there are many perceptual tasks that benefit from a continuous signal that allows integration of information over time. This is because some properties only become observable over time. So here's an example that illustrates this. This is an example thanks to Octavia Camps at Northeastern University in Boston. And what you see here is basically a soup of white things on black background. And only if I play this video for you can you actually see that these are dogs playing with each other. Furthermore, there's also evidence that understanding the concurrency of egomotion and sensing helps to develop meaningful sensory-guided behaviors. So here is visualization of an experiment done by Held and Hein. These two researchers basically raised a set of kittens in complete darkness, and these kittens were only exposed to daylight in this experimental setup that you see here. So basically on the right side of this experimental setup, you have an active kitten. That means that this kitten is actually walking through this environment while being connected to this carousel. And this carousel on the other side has a basket fixed to it, and in this basket there are the passive kittens. So these are the kittens who also move through the same environment, but they are not controlling this movement themselves. Okay, so while the kind of activity that these kittens are undergoing is very different, they are moving through the same range of visual stimuli. And the active kittens have control over this visual stimuli. The passive kittens do not have control. So the question is really, or the questions that Held and Hein ask is visually guided behavior influenced if these passive kittens, for example, are deprived of any kind of other visual stimuli, or if they are deprived of actually having control over these stimuli. And what Held and Hein found is that self-produced movement with concurrent visual feedback is really necessary for the development of visually guided behavior. And the way they tested that is by letting these kittens, the active and the passive kittens, basically do a bunch of independent sensory motor tasks like walking along a cliff or basically not walking against the wall and things like that. And the passive kittens were pretty bad at those, while the active kittens were behaving just normal and could do these fairly simple tasks. Okay, so let's give this kind of active phenomena of perception a name. Let's call it interactive perception. What this means is basically that we want to represent a perceptual signal in the combined space of sensory data and actions over time. And in robotics, the interesting thing is that we actually, have control over these actions to create a signal in that particular space. And this ability to control the actions and therefore influence how sensory data kind of evolves over time allows us to actively test any kind of hypothesis about the environment. So if you are a robot basically understands the structure in this combined space, you can really improve perception. For example, when you exploit this, for example, by physically interacting and creating a richer signal that would otherwise not be present, you could also infer latent properties of the environment that only become observable through physical interaction and motion. And you could also plan goal-directed actions if you know how your actions influence the state of the world. So really, this is a pretty old insight that has already been gained within robotics in the 80s and pioneered by, for example, Jeannette Bohg. We wrote a survey on this subject, emphasizing on physical interaction between an agent and the environment. And this survey really provides a framework, also a way of thinking about this space. And we are specifically looking at robotics and put robotics into relation to computer vision and active perception. All right, so here's one way how to think about this space. One way how to think about it is as a predictive model. It takes in sensory observations and also the actions that the robot performs, and from this it predicts the effect over time. So once you understand this, or once you have this kind of model, then you can use it to plan actions in a goal-directed way. For example, by plugging in this model into a model predictive controller. Okay, so that's one way on how to think about it. The traditional way to do this is through modeling physics. And basically, again, you take as input the robot actions, but also some kind of physical parameters of this process, and then you predict the effect. And here's some very complex examples of very complex object dynamics that are derived through complex physical modeling. And as you can see, it looks very nice. These are all these floppy fishes. And soon there's like a squid or an octopus actually landing on them. I don't know why that is. Here is a model of clothes that looks very realistic and interesting. And we also know how to model non-Newtonian materials. So all of these things look very nice. But yet when comparing these kinds of physical models to the outcome of a real physical systems, these models are typically inaccurate and don't capture the stochasticity of the real world as visualized here for a very simple example of planar pushing. So here you see the outcome of the real system on the left and the outcome as predicted by the analytical model on the right in blue, and there's quite a big difference. So the problem with applying these physics-based models is that we don't have access necessarily to the real values of the state or model parameters. The models are typically approximate, and they may be very expensive to compute, and they may not reflect the stochasticity of the real world. So recently people have turned more to purely data-driven models. They typically go directly from pixels to effect or even directly to observations. The processing of this data is really learned and kind of merged with the prediction into one piece, this learned model. So here's an example of such a work. This is from Chelsea Finn in 2016 with a reference down here. So this looks actually pretty interesting. But the big question for me is like how well this model actually generalizes outside of the training data. The question is really how would you ever be able to sample all that space to get enough data, and what happens if you replace the gray box with a green box or a slightly differently shaped box? So this is really the question here. So in this tutorial, I really want to explore or maybe shed some light on the question of what the perfect representation is and how to extract it from raw sensory data. This is really I would say maybe $1 million question. As I said, like this tutorial is in no way complete. I hope nevertheless that it's useful to those interested in the subjects from the viewpoint of robotics. So here are the questions that I'm going to go through in this tutorial. First of all, I want to shed some light on, or actually define what actually a representation means, and what a state is, and how are these two terms connected. And really, the state is essentially the interface between raw sensory data and the particular, maybe predictive model. And the state can of course be represented in many different ways, this is the next question that we're going to explore. What are the different kinds of representations that we can pick here? And this representation, so this interface between raw sensory data and the model, may really be learned directly, or it may be hand designed. So in many robotics decision-making and control tasks, you have a very good idea of what you want to know about the environment or an object. So for driving, for example, you may be interested in the pose and the size and the type of all the actors in the traffic scenes. You may want to know the lanes, the traffic signals, what is foliage and what is not. In manipulation, you may be interested in the 6D pose of an object or similar. And in general, in navigation, you may just be interested in where you are in the map. So in all of these examples, you have a pretty good idea of of how you want to represent the state. And these representations are typically, therefore, hand-designed and explicit, meaning you understand the manifold on which they are living. And they are also interpretable state representation. They're related to physical quantities that may have very well understood boundaries. Okay, so that's one type of representation that works well for these kinds of well understood systems. But for other cases, you may actually not know how to best represent the state or compress it. Examples are deformable objects like sand or toothpaste, like we've seen before, material or texture, or what kind of object parts are good to grasp, and so on. In that case, it might actually be useful to learn the most beneficial representation of features in the raw sensory observation, and these should be somewhat related to the task and what the robot actually wants to do. So we're going to discuss this. And then I will also discuss the question of how we can actually estimate the state from raw data. And so in this case, it really also depends on the state representation that we have picked. But if we use a hand-defined model, we may actually learn how to map from raw sensory data to this particular representation. For example, object detection is such a case where you want maybe the bounding box and the pose of this bounding box and the dimensions from raw sensory data. Or we may learn a representation on how to extract it from raw sensory data simultaneously. So this is also called representation learning. Okay, so and the last question we're going to look at is what kind of data we can process and how. So a robot typically comes with an entire suite that delivers structurally very different kinds of raw data. There may be, for example, RGB cameras that deliver images at, 30 hertz, but there may also be force-torque sensors that provide 60 forces and torques at kilohertz. And now, so you have this very heterogeneous data. How do you process these different pieces of information? How can you fuse them? How can you take in an entire stream of data? And this is also an interesting question that we will discuss in this tutorial. So this is the outline of this tutorial. I hope you are interested in learning more about these questions. And if your answer is yes, then please come and watch the other parts of this tutorial that elaborate on all of these questions. Thank you.